Welcome to this video lecture. Myself Atul Kumar, working as an assistant professor in Department of Computer Science, Rajiv Gandhi Memorial, Government College, Jogindarnagar. In this video lecture, I will discuss the remaining flip-flops. So, next flip-flop is D flip-flop. So, as we have seen in case of SR flip-flop, when both the input, that is S is equal to 1 and R is equal to 1, then the output in that case is unstable and the condition is called race condition. So when S is equal to 1 and R is equal to 1, the output becomes unstable in case of SR flip-flop, and the that condition is known as race condition. So in case of D flip-flop, there is no racing condition, and D means in case of D flip-flop is delay flip-flop. So in case of D flip-flop, we have a single data input, that is D, and a clock, that is C. As we have seen in a logic symbol of D flip-flop, we have a single data input D and a clock CLK, and the output here is Q and Q bar. The truth table for D flip-flop, in case if the clock is low, then there is no effect of input on the flip-flop, and in case if the clock is high and the input is 1, that is D is equal to 1, then the output is 1, and in case if D is equal to 0, then the output also becomes 0 in case of D flip-flop. So this one is the logic diagram for D flip-flop. So D flip-flop are created by inserting a inverter between S and R flip-flop. So there is a NOT gate attached to S and R flip-flop, and the input becomes D, and this kind of flip-flop is called as D flip-flop. And if the clock is high, if the clock pulse is high, and if the input is D is equal to 1, then output also becomes 1, and if clock is high and D is equal to 0, then output goes to 0. This one is the characteristic equation for D flip-flop. As we have seen, this one is a K map, and for K maps, suppose this one is D, this one is a D bar, 0 represent bar, and this one is a D, this one is a Q bar, and this one is a Q. As we have paired two ones in case of K map, so here the common element is D, and the characteristic equation so in case of D flip-flop is QT plus 1 is equal to D. Next flip-flop is JK flip-flop. So as we have seen in SR flip-flop, the output is unpredictable when S and R both are equal to 1. So to overcome this problem, we used JK flip-flop. JK flip-flop are widely used flip-flops, and the input used in case of J and K, J and K are the two inputs as in case of JK flip-flop. So JK flip-flop allows inputs when J and K both are 1. In that case, the state of output is changed and the complement of the previous state is available at the output terminal. So this one is the logic circuit diagram for JK flip-flop, and we have seen they are realized by making S is equal to J dot Q bar, that is Q dash, and R is equal to K dot Q. So when we given input S as J and the next input is Q bar, then and the input to R is K and Q, then this becomes a JK flip-flop, and this one is the logic circuit for JK flip-flop. So the truth table for JK flip-flop, when both J and K are 0, then there is no change in the last state, and when J is equal to 1, K is equal to 0, then the output becomes 1, when j is equal to 0 and k is equal to 1, then output becomes 0, and when both j and k are 1, then there is toggle. That is, if the previous input output is 1, then it is changed to 0, and if the previous output is 0, then it is changed to 1. So this one is the complement of the previous state. So in when j is equal to 1 0 and k is equal to 1, this one is the first condition. So if j is equal to 0 and k equal to 1, in this case the output of first AND gate becomes 0 and output of second AND gate becomes 1. And we have seen in case of SR flip-flop, when R is equal to 1 and S is equal to 0, then there is equal Q is equal to 0, then there is Q is equal to 0, that is the flip-flop in the reset state. So when j is equal to 0, k is equal to 1, then the output of upper AND gate becomes 0, and the output of the lower AND gate becomes 1, that is high, and in this case flip-flop is in reset state. And if the flip-flop is already in the reset state, that is already q is equal to 0, then R will be low. In that case R will be low and the flip-flop will remain in the reset state. In the second condition we have when j and k both are 0. Suppose we have j is equal to 0 and k is equal to 0, and this one is a AND gate, then the output of AND gate becomes also 0 if one of the input is 0. So this one is 0 and this one is 0. So input to S and R are also 0. So S is equal to 0 and R is equal to 0, and we have seen in case when both S and R are low or 0, then there will be no change in the output state. So it will remain in the previous state. So the third condition in the table, when when j is equal to 1 and k is equal to 0. Suppose here j is equal to 1, k is equal to 0. So output of lower AND gate becomes 0, as one of the input of AND gate becomes 0, so its output is 0. So R is equal to 0 in this case, and the output of suppose q is equal to 1, q bar is equal to 1, so the output here is 1. So output of upper AND gate becomes 1 when j is equal to 1 and k is equal to 0, and in this condition the output becomes q is equal to 1. So the flip-flop in the set state. And but the condition is if the flip-flop is already in the set state, that is q is equal to 1, then in that case S will be low, and if S will be low, R is low, then the flip-flop remains in the previous state, that is in the set state. The next is when both S, J and K are 1. When both J and K are 1, then flip-flop can be set or reset depending upon the state of the output. Suppose if Q is equal to 1 and Q bar is equal to 0, then the upper AND gate becomes 1, upper AND gate becomes disabled because q bar here is 0, so its output becomes low and the lower AND gate becomes enabled. So in this case S becomes 0, so S is 0 here, and R is equal to 1, and S is equal to 0 and R is equal to 1. In that case flip-flop in the reset state. So Q becomes 0 and Q bar becomes 1, and if Q is equal to 0 and Q bar is equal to 1, and S will be 1 and R is equal to 0. In this case S flip-flop in the set state, that is Q becomes high and Q bar becomes low. So when J is equal to 0, J is equal to 1 and K is equal to 1, then flip-flop can be reset or set depending upon the previous state of the output. So this one is the correct K map for JK flip-flop. So in this case we have make two pairs. One pair is this and the second pair is this. So in order to write the characteristic equation, it can be written in this way: qn plus 1 equal to, suppose in for the first pair, the common element here is qn bar, so we have written qn bar, and also in this case jk and jk bar, the common element is j, so j dot qn bar is the for this pair, plus for the second pair the common element is qn. First is there is qn, and the next common element is for first and last, the common element is k bar, so k bar dot qn. This one is the characteristic equation for jk flip flop. qn plus 1 is equal to j dot qn bar plus k bar dot qn. So there is also a race condition in case of jk flip flop. So in we have seen when j is equal to 1 and k is equal to 1 and q is equal to 0 and clock is high, then there will be a change in output or toggle in output. But we have there is a clock pulse, and suppose the clock pulse have a width of tw is applied, then after a time interval, suppose delta t, the output will change to 1, and after the time delta t we have taken j is equal to 1 and k is equal to 1 and q is equal to 1. So again after a time delta t, q becomes 0. So output toggles as 1 or 0. At the end of the clock pulse, the q is uncertain, and this condition is called race condition. So in case if when we j is equal to 1 and k is equal to 1, and if the width of clock pulse tw is low and clock pulse is high, in that case after a time delta t there is toggle or complement in the output, and at the end of the clock pulse, because the size of the clock pulse is high as compared to the width tw, that is the time interval, and at the end of the clock pulse we don't know what is the exact output, what will be the output, either it may be 0 or either it may be 1. So this condition is called as race condition. So how to avoid a race condition? So to avoid a race condition, the width of the trigger pulse is greater than the propagation delay of the flip flop, then in this case output is unreliable. So if tw is less than delta t less than t, if this condition is fitted, then in that case race condition will be avoided. The next flip flop we have t flip flop, and t means it is called as toggle flip flop. Toggle means to switch over to the opposite state. Toggle means if the input is 1, then it is changed to 0. If input is 0, then it is changed to 1. So toggle flip flop can be realized by using jk flip flop by making t is equal to j equal to k. So this one is a logic circuit for t flip flop, and it is formed from the jk flip flop by making t j and k equal to t, and there is the next input is clock pulse. So this one is the truth table for t flip flop. In this case, when t is equal to 0, then there is no change, and when t is equal to 1, there is toggle in the output. So this one is the logic diagram for t flip flop. As we have seen, this is the logic circuit for jk flip flop, and both the inputs to the JK flip-flop are attached to T, and to become it as a T flip-flop. So this one is the characteristic equation for T flip-flop. As we have seen, there is two ones and there is no pairing. So suppose this one is T, this up on the upside we have written as T, and from the downside we have written Q. So this becomes Q bar, and this becomes Q, and this becomes T bar, and this becomes T or T dash. So for this one, the characteristic equation becomes, the common element here is T and Q bar, T Q bar, and for the next one, the common element here is Q and T bar. So the characteristic equation for T flip-flop is T Q bar plus T bar Q. Next flip-flop we have master slave flip-flop, and in this kind of flip-flop we have used two flip-flop. One is called as master and second one is called as slave. So when the clock is high, the master is active and slave is inactive. In case when clock is high, then master is active and slave is inactive, and the master sets or resets according to the state of input signals, and as the slave is inactive during this period, its output remains steady at the previous state. When the clock goes low, means when clock is high then master works, and when clock is low then master is inactive. Then when clock is low, the slave is active and slave works. So when clock is high, master works, and when clock is low, slave works, and the slave sets or resets according to its input. The final output Q of the master slave is the output of the slave. So when clock is high, master is active and slave is inactive. When clock is low, master is inactive and slave is active. And as we have seen, when clock goes from high to low, then the output, the final outcome of master slave depends upon the output of the slave flip-flop. So this kind of flip-flop helps in avoiding the race condition in JK flip-flop when it can be triggered only once within the clock cycle. So there is no race condition in case of master slave flip-flop. This one is the logic circuit for master slave flip-flop. As we have seen, there are two flip-flop, one is called as master and other is called as slave, and when clock is high, this master flip-flop is active, and when clock is low, then this slave flip-flop is active, and the final outcome of this flip-flop depends upon the outcome of the slave flip-flop. And this kind of flip-flop are very ideal for counting devices, so they are very useful in case of counters. So next, what are the different applications of flip-flop? So as we have seen, flip-flop are mainly used for the storage. So they are very widely used for storage memory in case of registers. The second application is in case of counters, to count the number of clock pulses in the digital computers as a counter, and they are also very useful in case of working design of basic computers. And next application is they are very widely used as a frequency dividers. Frequency dividers means they are used to divide the frequency of the input clock. So these are the various applications of flip-flop. Thank you for watching this video lecture.